All right. Super. Can I get you to pick one to put up there? Your choice. Okay, so we've got one equation up there. No.
Okay.
So just a little bit of geometry here.
That is disgusting.
That's. There we go. There we go. There we go. Okay, that works. What else do we
You
have?
can put the square
Oh,
on there.
thank you, Tom. That'd be awesome. Okay, we got the square, we got the semicircle. Anybody want to venture any of the other equations for me?
Alright, so
We got the semicircle and the square.
you don't know.
Anybody else got one for me? Tell somebody.
Hey Jacob, you there?
What other geometric shapes do we have? Find the area of. Anyone give me any other answers? Harvey? Yeah, if you could, please. That'd be super. Thank you. Only know which one's gonna be left. Yeah. Why? Because I don't know it. Okay, so those three, if you didn't know them, you probably could figure it out pretty easily. The last one is an equilateral triangle. Anybody know it? It is 1/2 base times height. What is the base?
X.
What's the height? Don't say x.
The height.
Yeah, we have to find that, right? This is the ultimate in geometry. Here's my height. Right, we know the base is x. How do we find our height though? It's a 30, 60, 90 triangle. It's two of them, right? Back to back. Okay, so we have to do a little Pythagorean theorem here. If we have a 30, 60, 90, let me try to draw just one of those. Okay, the hypotenuse is how much? That's this, right? This is how much? Half x, right? It's half the bottom, and the bottom is the same length as the sides. So I have to find my height. I have to do some Pythagorean theorem. So what do I have in terms of Pythagorean theorem here? Which one's the hypotenuse?
X.
Yeah, right opposite the right angle. One of these sides here.
A squared plus 1 x squared equals x squared.
Yeah, h squared plus half x squared. How much is that if I square everything in one step? Yep. 1/4.
X squared.
Yep, x squared over 4, I'm going to call it. Okay, and then what's that squared?
X squared.
X squared. So that's like saying 1x squared. So if I subtract x squared over 4 from both sides, what do I have left? I've got 1 minus 1/4. Think about a whole pizza, take away a fourth of it.
3/4.
Yeah, 3/4 left, right? I always relate things to food. Square root both sides, what do you have?
Height equals 3/4 x.
Height equals,
Not 3.
not 3/4 x, good. What's the square root of 3/4? Square root of 3 over 2? Does that fraction sound familiar? Kind of triggish, right?
It's already
'Cause-
Circle.
Because, yeah, right, because we're talking about really a 30, 60, 90 triangle, which is inside a unit circle. Okay, so bringing it all together, the base is how much of the whole triangle now? The base is how long?
X.
X, right? It's the whole equilateral triangle we're trying to find the area of. The height is square root of 3 over 2x. So our area here is,
1/2 X.
what's half times square root of 3 over 2?
This can be like 4.
Awesome. Way to jump in. So there's the area of an equilateral triangle. Square root of 3 over 4 times x squared, x being the length of the side. Okay. So the reason why these geometric shapes are important today, particularly, is because what we're going to do is we're going to have an enclosed region, just like we have had all week long. We're going to have an enclosed region, but instead of spinning it around a line, we're going to take that enclosed region, stick it on the tabletop, and we're going to build up from that with geometric shapes. The geometric shape might be a square, it might be a semicircle, it might be a equilateral triangle, or a rectangle. But we're going to take that enclosed region, kind of like just put it on a dry erase board, lay it down on your surface, and then build straight up from it. And so if we do that, we get something that kind of looks like this. It's probably easier to look at on your PDF. These are just kind of rough things I pulled off a Google search. But we can see that we have, here's the origin, here's the function, y equals x squared. There's the function y equals x squared. Okay, we've got the x-axis. We've got the x-axis there and the y-axis. I get my origin there. And then it stops somewhere out here. I'm not sure where. But you can see when we lay that region, that enclosed region down, you can't see the enclosure here, but we stop the region there. When we take that enclosed region and put it on a horizontal surface, we can start building up with these geometric shapes and creating this solid. So if we take y equals x squared, we know y equals x squared gets farther and farther away from the x-axis as x gets bigger, right? It's a parabola. And so if we build this with, in this case, squares, these squares are going to get taller and taller as we get to larger values of x. And so we get this shape that comes to a point and then grows up like this. And that top of that shape is the top of all those squares. So it's a flat surface whose length is how long? If I take a generic square here, and let me use a different color. If I take a generic square here, trying to grab one of them, how wide is the square's base? Relative to the functions. It's as wide as the function is at that point. So if I make a square, then the square's height is also as wide as the function, okay? So if I start stacking all these squares, and we're actually going to do this after the AP exam, if I start stacking all these squares next to each other, and glue them together. We'll physically do that after the exam. And then make the contour so that the height is always the width of the function. We'll have this nice solid shape. And so we're just stacking those areas. We're accumulating that area across this x-axis. And so when we think about that then, accumulating that area across the x-axis is exactly what our calculus formula says. So that calculus formula, that integration formula, we've been looking at it, bless you, all week long, really does say accumulate those areas across the x-axis. So instead of this being rotated and we were forced to make a circle of pi r squared, in this situation we're not forced to make a circle. We're not rotating anything anymore. We're just literally accumulating that area. And what is that area? Is it a square? Is it a semicircle? Is it a triangle? We're just going to accumulate that area over that interval. So looking at this then, going back to that page, if we look at the square, the area of a square is what? What did we just find the area of the square as? Right? X squared, that was this. If we take a look at this, what is the length of this side now? How high the function is, which is x squared. So the area of this is the side squared. Maybe I shouldn't have used x. Maybe I should have used the side s squared. And that's x. The side is x squared. So this is going to be x squared times x squared, which is what? X to the fourth. X squared squared. So there's the area of that square in my picture. So if we're just going to accumulate all of those areas across the x-axis, then our integral is going to look like what? To find the volume of that solid. What's our area function? X to the fourth. Dx. Where did we start accumulating the area? 0. I'm not quite sure where we ended. Let's just say we end at 3. I'm not sure where it ended. How easy is it to integrate x to the fourth? Pretty easy, right? These should be pretty easy to integrate. Okay, so they would show up on maybe a no calculator. Okay, what is the integral of x to the fourth?
X to the fifth divided.
Yep, x to the fifth divided by 5, right? Bump up that power, divide by that new power. So if we have to evaluate that at 3 and then subtract the value at 0, anybody know what 3 to the fifth is? Big. That's,
Oh.
yeah.
What's 81 times 3?
Yeah, that's exactly what you have to answer.
243.
243, awesome. Way to power that through without a calculator. Okay, minus 0, just for kicks and giggles, we'll make sure you realize that that is in fact the case. Because we could start it at 1 instead, right? Chop off that first section. So we have 243 divided by 5 units cubed. Okay, for the volume of that solid.
Wait, isn't this just the area?
No, this is the volume because we accumulated the
Yeah,
areas,
yeah.
right? We set up all of those squares from 0 to 3. Okay, so after the AP exam, we're literally going to take our dry erase boards, draw our region, and I'm going to give you 1-inch thick insulation and put it together. And you're going to make sure that insulation is an overestimate so that you can shave away the stuff outside of the solid, and you'll actually physically make this solid. Okay. How are we doing so far? So what's going to come back now are these 3 free response questions I've been showing you over the past couple of days and putting X's through the stuff I didn't want you to do. Now we're going to do that stuff. So remember this, you remember this free response, right? Okay, so we had the sine function and the cubic function. And it's a graphing calculator one. And so what we're going to do is, this is going to be our enclosed region that's sitting on our tabletop. And we're going to build straight up with squares. So the question is, if we build straight up with a square, so we're going to try to put that square straight out there. Okay, I kind of missed it a little bit. There we go. If we build that square straight up, how long is that side? How do we determine how long that side is? Yeah, it's going to be this long. Is that the width of one function? Both functions? How would we figure out the length of that side? How do we figure out how long that side is?
Find both these points. Why is that?
Yeah, find both these points and do what? Do we add them? Do we subtract them? How do we find the distance between 2 points? We subtract them.
I guess we subtract.
Okay, so I understand what you're saying, Tyler. Tyler keeps saying add them. But he's thinking of this as a positive distance. Okay, it's really a negative distance in the function world, right? It's in the 4th quadrant. It's really negative. So by calling it positive and adding it, what we're mathematically doing is just subtracting a negative. Subtracting a negative function value is the same as adding, right? Okay, so we know that we need to take this, I'll call it y1 and y2, and we need to subtract them. Now, what is y1? Which function is that?
That's the sine.
What is 0 at 0 and 0 at 1
Sine pi of x.
and 0 at 2?
Sine pi x.
Sine pi x. So that's sine pi x minus, and then the other one. Make sure you use your brackets because we have to subtract that whole function. So there's one side. Which means, what is the area then? What is the area? Of this square,
That square.
the side squared, right? So we're going to have to take this and just stick some big brackets on either side of it and square it. What mode do we need to be in if I'm going to have to do an F int on this? Radian. How come?
Because pi x.
Because
Sine pi x.
Yeah, we have a trig function here. And we know that our trig values are always measured in radians. At least in calculus they are. Okay, unless you really specifically see that degree symbol. So there's our area. So what does this integral then look like? Where are we stacking these squares? Where are we starting? Where are we ending?
0 and 2.
0 to 2. And is our sine function always the bigger function over that entire domain?
Yes.
And is our cubic always the little one?
Yes.
Yeah, and that we won't flip flop. I know we did that with flat areas, right? We won't crisscross these regions at all, so that we don't have to split this up into more than one integral. So we know then, if we go from 0 to 2, we're going to stack these areas. So we just take that area function. And we're just going to go ahead and integrate that area function. Now, how do you want to do that using your fint? Do you want to use your vars key and put some things in your calculator? You can. Okay, if you know how to do that, sometimes it helps. You don't have to though. So why don't you go ahead and calculate that, the volume of that solid. Okay, and I'm just going to try to scroll down while you do that to give us a little more space. Okay, so just a quick practice on putting that into your calculator. If you think you might want to use the vars key, let me know. I can refresh your memory. Awesome. I just learned how to update operating systems, and I was having some problems.
Okay, what were those videos you guys were saying?
So I'm going to try it. I'm going to just calculate it first. Then I'll update your operating system. I just don't want to do that to your
Yeah.
500% of the
Thank you.
Sure. Okay. So if you want to use the vars, let me know. I can show you how to do that. Anybody getting an answer? So this stuff that we're working on is all this entire chapter is that chapter 6. Okay. The one thing that BC does that he doesn't do is it does double facts. So the last you just have to solve functions y and put in that y expression and do a dy.
So if you had a square root of x and y.
I don't understand this.
Yep, that's it. Yep, that's it. Okay, so put a units cubed on the end of that number. Yep, that's it. Awesome.
I was going to. It's like it didn't have a little box integral thing. I don't like it. Oh, it's alright, I got one that doesn't have it. Maybe.
You're not paying attention to the whole thing.
I don't.
Well, we found that, and now you gotta integrate that.
Just,
Yeah.
sort of thing. You want to get those easy points.
I don't understand how to use that.
That's it. Okay, so if we are getting 9.978 units cubed, then you're doing okay. Doing okay. You want a calculator?
No, I haven't looked at those. I don't know how to use that. So I just not going to.
Oh, I'm gonna update my operating system.
Is that correct? Can I be back? Really? I remember when I used to be
So you got one side. All right. So this one, Interestingly enough, this is still in a graphing calculator problem. But this one is saying set up but do not solve, okay? So we always have to be cognizant of this and not waste time solving something we're not being asked to solve. So here's the function. Go ahead and set up and solve. Each section perpendicular is still a square. Okay, so go ahead and try this one. We're still going to set up a square here. Okay, so a little big tall square coming back down again. Go ahead and set that one up. Yep, that's it. You got it. How do you know to use a square? Because it tells you right there.
Which one's cosine? Which one's
So, yes, it will always tell you. Otherwise, you wouldn't know what shape to draw. No, it doesn't matter what you draw. Because remember, the whole idea of integration is accumulation, right? So we're going to accumulate those squares starting
The
at
next
the
one
y-axis
is
and accumulating them all the way out to t. Sure. So this shape is going to be really pointy at either end as those squares go to what area value? 0, 0, and 0, and then they're going to get bigger. And if you can find the area of that, the portion of that region with the biggest gap, that's going to be your tallest square. And then it's going to scooch back down again. It's going to be a flat top because the tops of squares are flat. It's going to be a flat front and back because the front and back of the square is flat. And so those surfaces are going to do this sort of thing and do this sort of thing. I'm working on a GeoGebra file that will generate these 3D shapes. I still haven't worked out the coding for that though. I'm still trying to kind of learn that out as well. Well, the square is telling us that we know to find the area function, okay? So to find our area function, we're going to have to determine the length of that side. Okay, so we're going to have to take the difference of two functions again, right? And so we're going to have to take that length, I'll call it S, and square it. Well, we know that length is going to start at 0 and then have some value and end at 0. And that value is going to be dependent upon where this curve is and where that curve is. So again, how do we find the distance between 2 points?
subtraction.
By subtraction, right? And we're going to have to subtract equations. How do you know where it doesn't matter. Is this point always going to be on this function?
So you basically just picked a point on each
Yep.
function.
Yeah, I'm just picking these 2 points because I want to draw this perpendicular to this axis.
So any perpendicular line, even if it's like on the other side, you can use.
Yep, like right here?
Yeah.
You could, but it would be
Well,
outside,
I
it
don't
would be
really-
outside the interval,
What
but
about
yeah.
like farther down on the other
Right
side?
here?
Like, yeah.
We could draw it right here. It would just be a smaller square because those are closer together.
Okay, so this doesn't matter. Just
Well, because that's going to tell us how wide the bottom of the square is. So in other words, if we go back to this sketch, the distance between the 2 functions is going to tell us how wide the bottom of our square is. So close to the origin here, these squares are really tiny because the gap is really small. Okay?
The point just stands for that function. It doesn't stand for one actual.
Not necessarily.
Okay, no, but like
Well,
you're
from
not talking about you plug in the function for that point.
Yep, you do.
That's the point.
you have to describe it.
Okay. So what is the top function? What is the bottom function? Okay. So how long is that? This distance between the points. Okay,
Yeah, I do this.
so if we look at those 2 points on your sketch,
It's right here.
yeah, we want to subtract the 2 functions. Okay? So our functions are f and g in this problem. If I had to label this top point, is this function f or is this function g?
I'm gonna say G.
It is. This is g of x. Okay, this is our cosine. How did I know? Well, okay, you have a calculator, graph them. One way. Okay, I look at this and I say that's a parabola that opens up. So I know it's got to be this thing. This is opening up. So this is f of x. So our side length then is what? If we have to subtract those 2 points, we have to do what? What function minus what function? Yes. G of x minus f of x. Exactly. Okay, that's that top point minus that bottom point. We're back to top curve minus bottom curve. Okay, so we have 4 cosine 1/4 pi x minus that whole thing. 2x squared minus 6x plus 4. Now this one might actually be beneficial to put one in y1, the other in y2. And do a vars thing. This is getting kind of a lot of brackets here. Okay. So, yeah, that's just the side. It's getting really lengthy. Yeah, that's just one side. So the whole area is squaring that whole thing. So I just stuck big brackets on both sides and put a square up there. Okay. So I can kind of cheat here. There's the area. So I can just go ahead and stick my integral function here and my dx there. And where am I stacking? 0 to 2. There you go. Okay. And then all it's asking you to do is set it up. It's not asking you to find the answer. So don't worry about putting that into your fnt. Okay? Don't need the answer to that one. All we need is the setup. So make sure your integration sign there, your limits are there, your dx is there, your brackets are there. F pi r squared. Is that the radius?
Yeah, because this right here, no. Would it just be 20?
If you have this, but then you just need to draw your semicircle like this. This way, along the, yeah.
So like this?
Yeah, you don't have to go, it just says set up. Yep.
So like this?
Yep. And so, from orange to purple, is that the radius?
Yeah.
It goes all the way across the circle, is that a radius?
How do you find like which line you're supposed to? Oh, it's a diameter.
It's a diameter, yeah. That's what we're doing next. Yeah. Okay, so back to this one that we did yesterday. And so if we look at this again, careful reading, cross sections perpendicular to the x-axis. So they have to go from orange to purple. That's perpendicular to the x-axis. And semicircles. So we know that the area of a semicircle is 1/2 pi r squared. Okay? If we draw the semicircle here, so there's the bottom of the semicircle. So it looks something like that. What function is this? And what function is this? Okay, so I'll let you get that semicircle drawn. And then we're going to talk about those 2 points. Okay, if you're already calculating this, it's awesome. Okay, this top point is what? 20 divided by 1 plus x squared. The bottom dot is what? 2. Now, here's the tricky part. This is the radius. If I subtract these two and I get the distance between those 2 points, if I found a radius, I found a diameter. The radius is how much? Half the diameter. Guess what I'm going to do? I'm going to get the semicircle equation in terms of diameter. Okay? Because that way we can just throw the functions in there. So it is, instead of 1/2 pi r squared, it's how many times pi d squared?
Oh,
1/4. Right? A half times a half.
But isn't that half squared?
Oh, it's an eighth. Oh, wait a minute. 4th, 8th. Good catch. Okay. So when I set up my integral then, okay, how much is my diameter? Yeah, it's this minus this. Okay, and then I have to square it because it's my diameter. So I have 1/8 times pi, a lot of people call it pi over 8, times 1 plus x squared minus 2 quantity squared dx. Okay? And that does get a little tricky to plug into your calculator. Does anybody have an answer? I can't remember what it was off the top of my head, but I do have it here. I can scroll back up and take a peek. 174,268.
Oh, I got that.
Okay, so this is a do an F-int, so if you want to challenge yourself with that F-int, the answer is 174.268. Okay. So at this point, we're really done with the contents. Tomorrow we'll have our Blackboard quiz on section 7.3. See where you stand on that. Okay, so that's going to be washers and discs, right? Discs first, then washers, and then known cross sections. In other words, building straight up with a geometric figure. Okay. So at this point, the rest of the hour is, yay, yours. It takes a while to crunch through those numbers on your calculator. That's for sure. Yeah, I'll be right over. Okay.